Welcome back, everybody. This is part 2 of our One World seminar for this week. We have Jean-Christophe Mourrat from New York. Now, Jean-Christophe has asked to do things with a slightly different format. So we usually ask people to pose and even answer their own questions or be answered by other people in the audience. But Jean-Christophe will be, amazingly, he's got a split brain. He's going to be multitasking, watching the questions, and I might help you with that and interrupt occasionally if you've missed a good one. And he'll answer them during the talk. So please don't hesitate to ask your questions or kind of make yourself known to me by raising your hand in the middle of the talk.
So I don't have split brain. I count on you, Andreas, to help me to figure this out.
Okay.
So please feel free to interrupt me. I don't mind.
Absolutely. Okay. Well, let's get started. So Jean-Christophe is going to talk about disordered models and Hamilton-Jacobi equations. Thank you very much.
Well, thank you very much for the invitation. It's a great pleasure to be here. I see many friends in the audience, and it makes me happy to see you guys. I hope you're doing well. So today I'm going to speak about certain models of statistical mechanics which have disordered interactions. And the main point of the talk will be to highlight a connection between these models and certain partial differential equations, which are called Hamilton-Jacobi equations. So let's get started. So to give a setup, let's take independent Gaussians. And let's say that I want to understand the maximum over sigma, which is a vector of +1s and -1s of this sum. So sum over Jij, sigma I, sigma j. Sum over all I and j between 1 and n. Okay, so one way so I want to understand how this behaves when n becomes large for typical realizations of the j's. One way to think about the problem is you have n individuals, and for each pair of individuals, you have this Jij, which encodes the quality of their interaction. So if they really like to be together, Jij is positive and large. If they really dislike to be together, then Jij is negative and large. And you're supposed to split these people into two groups. So there's the group of the +1 and the group of the -1s. And you're trying to maximize the quality of the interactions within the groups, and assuming that the groups don't interact. So you see that the quantity that's displayed will capture the overall quality of the best possible matching over all one, right? Because sigma I, sigma j will be equal to 1 if you have chosen that the individual I and the individual j are in the same group, and it will be -1 if they are not in the same group. So it's just up to a constant factor. It's an encoding of the problem. So I want to think about that. And the main feature of the problem is that it's not possible to make each pair as satisfied as possible at the same time, right? If for instance, you have 3 guys, I, J, and K, and I want to be friends with J, J wants to be friends with K, but K does not want to be friends with I, then there's no way you can make every pair happy at the same time. So there is I could write down that there are frustrations in this problem. It's complicated and suboptimal, or at least it's not really suboptimal, but it's a mess to find the right optimum. And this really is the signature of glassy objects, like what physicists would call the glasses. So one word for these models is also spin glasses. Spin because there are spins, +1 and -1s, and glassy because there are these frustrations. So I phrase the question as about the maximum, but you can also make Gibbs measures out of this function, right? Like when you do with the Ising model. So if you want, it's like an Ising model, but the interactions are random. And in this specific model, every item interacts with every other item. So if I write down the Gibbs measure, that would be something that, it will be a measure on the set of configurations of +1s and -1s. And to each configuration, it will give a probability proportional to exponential of some parameter, which, okay, we can think about it, but let's take it for granted that this is the correct scaling, times this same function, sum of sigma I, sigma j. Okay, and more generally, I would like to understand the behavior of this measure, not just the maximum. So when beta becomes very large, the measure will be mostly concentrated on the maximum. So if you want, it's a soft relaxation of the maximum thing. And when beta is small, on the other hand, this thing will basically look like a uniform measure on all configurations. So it's not easy to directly confront the measure. So it's useful to first think of the partition function, which is what you get when you sum over all possibilities this quantity, sum over all sigmas of this exponential. And you try to understand the large scale behavior of this thing. And again, I'm not explaining the scaling very well, but inside the exponential, typically the quantity would be of order n. So if you want to understand the large scale limit, it makes sense to take the log of that then, and then to divide by n. Okay. And this I can expect converges to a constant. So notice that it's still a random quantity, right? It depends on the j's. So, but the fluctuations will be small. So I should not bother about it. But let's just to make sure they are not here. Let's take the expectation. Okay. So now it's a deterministic object, and I want to understand its convergence when n becomes very large. Okay, I want to understand what happens when n goes to infinity. And the striking thing, in my opinion, is that this is actually a very difficult question, and the answer is very non-trivial. And the first step towards understanding this thing was done by Parisi in the late 70s and subsequent papers. Oops, I did not write his name properly. Okay, apparently I cannot write his name properly. Okay, P-A-R-I-S-I. So it's in the physics literature, and he predicts a formula for this limit. And the formula is fairly complicated. The way it's usually written, I cannot even remember it easily. And in fact, initially also, I have to say, it was relatively controversial, even in the physics literature, that this formula was valid. So I think, part of the reason is that the manipulations involved are not just that, they don't do all the epsilons and deltas. It's a rather, at least initially, it was a rather wild technique. It was far from rigorous mathematics. But perhaps another reason is that the formula starts by looking like this. So it's an infimum over probability measures of some quantity. Okay, and if you think about it, it's quite counterintuitive that it's an infimum over probability measures. And the reason it's counterintuitive is that, okay, maybe first I take a step back. So when you have this sum over all sigmas, without really changing the problem, if I want, I can divide by 2 to the n. It's just moving everything by a constant, it doesn't matter. And so it's useful to think of this as a probability measure on the space of configuration. So it's your reference probability measure, if you want. And each time you have something of the form logarithm probability measure of exponential of something, let's call it f, it's well known that you can rewrite it as the supremum over probability measures of the expectation under this probability measure of that function f minus the relative entropy of that measure with respect to the product measure that we start from. So this is a very natural formulation from a physics point of view. You know, you have this energy, entropy, competition. The optimizer is the Gibbs measure, and all these things are related. So the thing on the left-hand side, you really want to write it down as a supernumerical probability measures, and on the right-hand side, it's an inferior probability measures. So surely something was wrong in this argument. But you know, as time passed, physicists understood more and more of this picture, and they became convinced that although it was counterintuitive, in fact it was correct. And then you know, for mathematicians, the definite confirmation arrived when we figured out a proof of this result. So oops, sorry, I wanted to not put it in green. So it came in two stages. So the first step was by Francesco Guerra in 2003. He proved oh, sorry about that. He proved one bound. Don't know what happened for this object, and then Talagrand proved the other bound shortly afterwards. And later also the proof was refined and extended to other models by Panchenko in 2013. And this, I have to say, I'm also hiding a lot of contributions by other people, including Eisenman, Arguin, Polthausen, Stickman, Roel, and others. So there's been a lot of work on this, and yeah, a lot of progress has been achieved. And so this is a known result. It's a mathematical result. And still, I want to talk about it, and I want to think about it more. So I have to explain why I want to think about it despite the fact that it's already a known result. And I think part of it is that I still find it confusing in some sense. I find I don't know, maybe I find it difficult to remember or something, or maybe I find it surprising that we don't seem to have the same language to speak about what is before we pass to the limit in n and after. You know, it seems that we don't have the same way to talk about both sides or something. I find it surprising. So that's kind of a fuzzy comment. So maybe to be more specific, it's also that I started to think about what happens in a slight variation of the model where you have these items. They are no longer completely interacting with no geometry. You have just very simple geometry. You will have just two layers of your spin. So let's say they look like this. And instead of having interactions between any pair, you will have interactions just every spin, every item interacts with every item in the other layer, but not within layers. Okay, so I'm not drawing all the links, but I hope you see what I mean. If you don't, you can scream in the chat. Sometimes I look. So the whole point is that this is not allowed. Okay. And in this case, I realized that I was not able to write the formula, and I thought, well, that is a sure sign that I don't understand what's going on. And so I tried to think some more about it, and what I'm going to present is the result of this trying to think about it. So I'm going to maybe I can pause. And are there questions so far? Are things going okay? Are you happy with the talk?
So far, nothing in the chat box. And Christina thinks you're doing a great job.
Okay, cool. Hi, Milton. Hi, Handel. Yes, so I'm going to present a precise result, but first I'll try to display the main message in some vague terms. So the main message is that there are these partial differential equations, Hamilton-Jacobi equations, and these equations allow to rephrase the Parisi formula. Oops. And I would argue they help to synthesize the results perhaps more easily, or at least as far as I'm concerned, I find it easier to remember in this way. And with this point of view, I think it also helps to clarify the nature of the difficulties we face depending on the model. So let's say clarifies the difficulties. So, you know, why is it that when I write the model with 2 layers, I just cannot figure it out, and when I write a layer with 1 layer, apparently we can figure this out. So I think this new point of view provides one way to understand what is going on, which in my opinion is clarifying. And finally, you know, perhaps once you manage to actually name your problem in a more clear, you know, in a clearer way, maybe you have a better chance to attack it concretely. So hopefully, you know, maybe you can prove new results. And also I will argue, although this is more uncertain, it's possible that this point of view is unavoidable for certain models. So maybe unavoidable. Like this model with 2 layers. So this is highly uncertain, right? I cannot mathematically justify that something is unavoidable, but it's just my take on this. Okay. All right. So now that I wrote down this sort of message, let me state a precise result. So the main result I want to present is the following. So let's say we fix some parameter. I just, instead of beta, I write t for some reason. So okay, we're studying this limit 1 over n, expectation, logarithm, sum over sigma of the exponential. So instead of beta, I write square root of 2t, this is a 2, divided by square root of n, times sum of jij, sigma I, sigma j, minus nt, equals f of t delta naught. Okay, so I'm writing it, and then I will comment on it. Yeah, so let me finish to write it.
Little question now. What's the letter before the t under the square root?
Oh, it's a 2. Yeah, that blurb here is a 2. Okay. I try to rewrite it 2. It's just a normalization. Okay, it's a convenient way to fix the parameter. It's just so instead of beta, I was square root of 2t, whatever, and also it's my fancy to add this extra nt here. So maybe okay. About this square root of t times the Gaussian, this feels natural, right? Because when you think, it looks like a Brownian motion. It's a natural scaling when we study Gaussians to to increase the variance linearly versus increasing the size linearly. And then if you think that this is Brownian motion inside the exponential, then you see that if you want to maintain constant expectation of the exponential, you should add a compensating term, which would be the quadratic variation, and this is this MT. So it's a natural normal way to normalize things, but you see that it's a constant, so you can just flush it through the exponential if you don't like it. So it's not very important.
There's another little question. Do you need a factor of 2 to the minus capital N?
Yeah, so that's also a good question. So I can add it or not. I actually find it more natural to have it, but for some reason I thought you would prefer to not see it, so I have not written it. So this also changes everything by a constant. And the equation does not see constants, so it will only change the initial condition, which I have not described. So the statement with the 2 to the minus n here is also valid. Other questions? So I did not explain very well. So on the right hand side, this is f at t, and delta 0 is the Dirac probability measure at 0, and so the function takes two arguments, this real parameter t and the probability measure. And the equation is solved is the one that is written here. It's the first order equation. So I think one thing I need to explain is what is this derivative thing? Like we have a function that depends on the measure, and we're differentiating with respect to the measure. What does it even mean with the Dirac? Yeah. Okay. So the function is Lipschitz with respect to the probability measure variable. So I mean, okay. Yeah, it depends how uniform is the convergence. Yeah, everything is Lipschitz, so it's locally it's pretty locally you have uniform convergence over probability measures. Everything is Lipschitz. And psi, yeah, is a secret. I'm going to give some more hints later in the talk, but that's a very good question. It will be clarified a bit later. So let me explain what this derivative is. So you can just think that every measure is a sum of Diracs. It doesn't matter, everything is very regular. Like anyway, let's just assume that the measure is a sum of Diracs. Oops, and it's hard for me to draw the vertical lines apparently, but okay. So this is the representation of the measure. I just draw a bunch of Diracs like this. And for each point in the support, so let's say this x here is the position of this specific Dirac, I'm going to define d mu f of this measure mu, which is drawn at position x, which is in the support of the measure, by just looking at the effect of wiggling around the Dirac at position x. So if you just pretend that all the Dirac sizes are fixed, and your function is just a function of the position of the Dirac, then it's just the normal derivative with respect to that position. Okay, so it's, I mean, if you're familiar with this, it's more like a transport type of derivative. You're moving mass around and you're checking the reaction to this moving mass around. All right, other questions? Yeah, what is psi? It's a secret. Yeah, so I want to make a few comments. So before I explain where this comes from, I want to make a few comments about why I find this result pleasant in some ways. Yeah, so the first comment I want to make is, there is this quantity here, which is really this energy function. Let me give it a name. Let's call it Hn of sigma. And you see that, I don't know, I have these things here. You have, really what is important is what is the covariance of this object. So if I look at two positions, so imagine you're doing this calculation about the covariance structure of this guy. So you will have the sum of Jij sigma j multiplied by sum of JKL, tau K, tau L, and all the correlations will vanish unless ij is equal to KL, right? Because the j's are independent. And what you get by doing that is the scalar product of sigma and tau squared. And then, okay, you have to keep track of the scaling. So this is, you can just trust me on this. But the point is that you get a function of the scalar product and you get it squared. And what's one thing which I find interesting is that if you change the function hn, for instance, if you were doing instead of jij sigma I sigma j, you could write 3 terms. You could write j ijk sigma I sigma j sigma k. Okay, and then what that would change is that instead of this exponent 2 here, you would have a 3. And if this happens, then all the result I just showed you would be the same, except this 2 here would be changed by a 3. Okay, so really what you're seeing in the, more generally, what you're seeing in this integral is just the function that drives or describes the covariance structure of your model.
Jean-Christophe, so there was a question.
Yeah, that's right, Julien. That's a good question. So the thing is, if you want, the derivative will be a very big vector, and I will index it by points in the support of the measure. So instead of writing it as a big vector, I write it as a function of x. But initially, you're right, the function it does not depend on x. But the derivative is this giant list of okay, awesome. Okay, and now, yeah, I made my point about the covariance appearing in the equation. Yeah, so maybe a last point. Yeah, and when this happens, when you change the covariance, the initial condition, which I have not described, does not change. So at least we don't know what it is yet, but it does not change. Only the exponent that is in yellow in the screen will change.
Sorry, these guys are relentless. So Hendrik is asking, does the derivative coincide with what?
Yeah, it's I think so. I think it's the transport derivative. Yeah, and that last comment is that if instead of changing the covariance of your function, you're changing this reference measure here, this 2 to the minus n sum over sigma, for some other measure, then in this case, what happens is that the evolution equation will not change. It will remain the same, and all the effect will be hidden in the initial condition that is here, which I have not described. But okay. All right. Are there further questions on this point? Besides the mystery of the initial condition. Yes, that's right. So the integral is with respect to x. So for each fixed mu, you can calculate this term in the equation, which is integral of d mu f squared of mu n x d mu of x. That's right. Thanks for the questions. It is really pleasant for me to feel that there is feedback. All right. So and now. I want to come back for a second to this model with 2 layers that I was drawing here. You remember this model with 2 layers. So I want to come back to it. So just to splash on you the equation that appears for this other model. So 2 layers. So this I cannot prove for the 2 layers thing. I can only prove 1 bound, but I believe it's correct. The equation in this case. So in this case, there are 2 layers, and so you will have to have 2 measures in your function instead of 1. So I call them mu1 and mu2, and the structure looks sort of similar, except that instead of having the d mu squared, it splits into the product of 2 derivatives. And it's not crucial that you really focus on on the definition, on the specific form of the equation. But what's important to notice is that the nonlinearity here is not convex, while in the equation that was displayed here on top, with the square function, that was a convex nonlinearity. And when you have a convex nonlinearity in these equations, it's well known, at least in the finite dimensional case, that you can write the solution in a variational form. Okay, it's the Hopf-Flachs formula. And if you want to bridge the statement I showed you to the formula that is used usually, that's the steps you can do. You start from the equation, let's say, then you write this Hopf-Flachs formula, and then you massage it somehow, and then you find their formula. But the thing is, this requires that the nonlinearity is convex. And for the two-layer model, the nonlinearity is no longer convex. It's like if you take a pair x, y, and you spit out the products x times y, this is not a convex function. That's all what I'm saying. And so for this model, there is no variational formula as far as I can tell. Oops.
So a quick question from Nat there. Why is it natural physically to think that this is a function of t?
That's a good question. I think of it as some sort of analogous to when you do a renormalization flow, but it's a bit unclear if it's a good analogy. It's like you're flowing from when t equals 0, where you understand everything is just the reference measure that is showing up, and then you progressively add what is difficult in your problem, and hopefully you understand the way this happens. But I mean, it's a bit of a shaky. Okay, that's my understanding. Right. So I suppose, although this I cannot justify, that in the case of the two-layer model, the best way to describe this free energy is by using the equation. There is no other way. So this was I described properties of the result, but not really why the result is true. And I'll try to explain it more clearly on a toy model, which is the Curie-Weiss model. So it will be very simple, and the model can be solved in a variety of ways, and to some extent, the way I'm going to solve it is a bit too complicated for the model, maybe. But the point is that the strategy I'm going to present, I think, is very robust to other models. So, for instance, I use this for models which are of intermediate difficulty between Curie-Weiss and the spin glass model, which come from statistical inference. And it worked very efficiently there. So, bear with me if you find the model too simple. I think it's still useful to think about it. So, the Curie-Weiss model is what happens when, instead of having these random interactions, you just assume that it's a deterministic interaction. Every j is equal to 1. So 1 over n log sum over sigma. Exponential 0. Sum of sigma I and sigma j plus h. Sum of sigma I. Okay, so I add the magnetic field also because I add this plus h sum of sigma I. I think it's interesting. So I removed the disorder. Then the scaling has changed a little bit, but it's because it's not disordered anymore. And really, I would, ultimately, I would want to understand the probability measure associated with this, which I will denote like this. So by definition, this is the sum over sigma of f of sigma exponential of blah, blah, blah. And blah, blah, blah is the same as above, divided by the sum over sigma of exponential of blah, blah, blah. Okay, so ultimately we want to understand the measure, but it's really useful to understand this function fn first. Maybe it sounds surprising to focus on this object first, but you should really think of it as it's the moment generating function of the quantities you care about. So if you understand the moment generating function, you understand your object very well. So that's one way to understand why it's useful. It's not the only one, but. So for this model, I want to display how equations will arise for Fn. And so let's just try to compute derivatives and see what happens. Let's say I compute the derivative with respect to h. Then, okay, there's the 1 over n in front all the time. Oops. And then you have this logarithm that you're supposed to differentiate. So after you differentiate, you have a ratio of the derivative divided by the function itself. And when you compute the derivative in h of this exponential, it's this sum over sigma I, which will come and show up in front here, right? So in the end, you will have something exactly of the form that is displayed here. Right? You will have this ratio, and for f of sigma, you will have sum of sigma I. So long story short, you find this, okay? And if you differentiate with respect to t, well, then the same thing happens, right? It's just that in this case, it's whatever is in front of t that shows up in your expectation. And because that's kind of the simplicity of Curry bias, you can rewrite this thing as in terms of 1 over in terms of the sum squared. Oops, I wrote squared a bit too many times. Okay, so if you don't look at this too carefully, you think that's kind of interesting. The time derivative is the square of the h derivative. So that's not quite true, but it's a good thing to make this mistake, let's say. So this really is the variance of this. I don't know why this happens. Of this mean magnetization, let's say. So it's not 0, but already what this magnetization is between -1 and 1. So it's already over the 1. And now we're looking at the variance of this thing. So if you're a bit optimistic, you think, there will be a bit of cancellations. This will be small. And so already it suggests to you that maybe as n goes to infinity, the function will solve the equation where you just put 0 on the right-hand side. And so you want to make this more rigorous. So I think the next question is how can you express this variance internally in terms of Fn? I said Fn is the moment generating function. So in some sense, it should encode information about the variance of this quantity as well. And I guess it's not surprising that if you take the second derivative of Fn, this will be related to the second moment of the variable of interest. So I'm not going to do this calculation, but it's not a difficult calculation. What you can see is that what is on the right-hand side, in fact, is 1 over n times the second derivative of Fn. And once you're there, in terms of, as it comes to understanding the large-scale behavior of Fn, you're really done. Like you can stop thinking about the probabilistic model. You have an equation for Fn. It's remarkable that it's an exact equation in this case. And now you can turn to your analysis friend and ask what happens with that thing. And
question from Luigi there.
Sorry, what did you say?
There's a little question from Luigi about the angle bracket.
Yeah, that's right. So implicitly, yeah, this bracket is a measure that depends on T and H. That's right. Yeah. Thanks for the question. And so for this specific example, we see that you can justify that Fn converges to F solution of dtf minus dhf squared equals 0. Yeah, and I have not talked about the initial condition. Again, I have this bad habit, but now I think it will be very easy to see that in this case, things behave really well. So let me go back to the definition of Fn. So here it is. And suppose for a second that t is equal to 0. So let me just dash this guy. Then you see that the expression becomes really nice because you have exponential of the sum. And so you can write it as a product. And then you can factorize, it's the sum over sigma, but this is it's a product measure, and then you have a product. So you can factorize this one more time. And once you have done all these manipulations, you discover that in this case, when t is equal to 0, the function fn, in fact, does not depend on n. Okay, so the initial condition, in fact, here is f at t equals 0 is f1 at t equals 0. And that property is also true for the spin glass case. So I have not really explained fully what's going on, but at least the fact that it's a one body, it's a non-interacting thing that shows up for the initial condition is also valid in the spin glass case. Yeah, and maybe once you see it, you're thinking, what do I learn about my probabilistic model from this PD? And this will have shocks. The limit will have shocks in its derivatives. When t is small, the function will be smooth as a function of h. But then after t becomes sufficiently large, you will have a corner in the function when near h equals 0 as soon as t is above some threshold. And that is significant because the derivative of this function, they capture this mean magnetization, the line on top of what is displayed here. So if you have a corner of the derivative, it means that when h is positive, that's very tiny, the mean magnetization is positive away from 0. And when h is negative, very tiny, magnetization is negative away from 0. So you see phase transitions in these singularities of the limit equation. All right. Yes, also, I think it's also a good time to add a comment about I forgot to say earlier, but in the theorem I showed at the very beginning, I would like to have an intrinsic approach. So the theorem about the spin glass, it's a theorem, it's proved, but in some sense I consider I cheated to prove it because I have not given a proof that starts from scratch and achieves this result using the PD thinking. I just wanted to check for my sanity, if you want, that the description was correct with the PD. So I just borrowed the formula that was already proved and just mess things around up until the moment I could verify that it also matches the equation. But ultimately, I wish that, and I think it's necessary that we develop an approach that just uses this PD thinking to prove the result. So that's still in development. And right now, I can only prove one bound, also for the bipartite case, but ultimately, I hope we'll have understanding along these lines. Are there further questions? I have very little time, but I will just sketch very briefly in 5 minutes how this behaves in the spin glass case. Everything good so far? You're still happy?
Quick one from Hendrik there.
Yeah, for easing on a lattice is going. I don't think you can easily wrap equations like this. Maybe I think there's an old paper of Chuck Newman where he may use some of intuition kind of like this to get bounds on critical exponents. But I think for lattice models, you probably can only hope for comparisons. It will not be the fact that we can completely wrap up the equation is a bit of a miracle, in my opinion. Maybe, I don't know if Julien is agreeing or not. All right, so back to spin glasses. So one thing which looked very innocent. So to some extent, I tricked you a little bit when I presented the Curie-Weiss model in a way which maybe it's when I wrote the first line, the very first line here, when I wrote the definition of Fn of T and H, I said, oh yeah, I'm going to add a magnetic field because why not? That was not honest. I had to add this magnetic field because otherwise I would not have managed to close the equation. If I just write if I forget to write this thing, I can differentiate in T to my Haas content. I will not manage to close the equation. So it looks very innocent for Curie-Weiss, but really the first step is to understand what are the quantities you're supposed to add in this energy function that ultimately will allow you to close the equation. And for spin glasses, it's a non-trivial question. And you see that it has two benefits. Like first, you can close the equation. And second, when you set T equals 0, it becomes a simple model and then you can compute it. So it has to have these two features of being sufficiently rich, but also sufficiently simple that you can compute what happens when only this term is present. Yeah, Simone, I agree. I thought it was Chuck Newman, but I agree with what you're saying. At least I think I saw a paper of Chuck. All right, so let me rewrite this quantity. And the point I was trying to make is now we have to think about what is this extra term we should be adding in this exponential. And one way to think about it is you can think that this term looks like this, and you're trying to find some effective model that captures this guy. Like you would like something that's like one body type interactions, that only looks at sum of sigma j's, and that somehow here has some term that represents this behavior. And maybe as a first pass, we could try to have a random magnetic field. And then there are the useless normalization things, which let's not care about this. Okay, so here I want these guys to be independent Gaussians. Okay, and it's my first try for adding a quantity that hopefully will close the equation. And now I'm going to just write down the formulas, but it's not difficult to make these calculations. So there will be a Gibbs measure associated with this exponential. And when I compute the derivative, what I find is the following. So this is the scalar product between sigma and sigma prime. And sigma prime is this thing is an independent copy of sigma. Okay, under I should write under the Gibbs measure. Okay, so it comes by doing some Gaussian integration by parts. And when you differentiate in T, what you find instead is expectation of sigma dot sigma prime divided by n squared. And so it looks very promising. It looks like the Curie-Weiss model. You're thinking, haha, now I know, probably dt fn minus dh fn squared is going to be close to 0. And but this is not true, unfortunately. That's the problem. It's still a variance. It's the variance of this scalar product of this overlap, but it's not true in this case that the overlap has a small variance in general. It will only be true for small t. So for small t, the equation will be valid, but only for small t. And so I should say also that this intuition is not mine, right? It's been developed by many people. You can see it very nicely written in the paper of Mourrat, for instance, or many places. So like the intuition of Parisi, Mézard, and physicists also is that the overlap is not going to be concentrated, and instead it will have a more complicated structure. And so I go back to here. So the message here is that this guess that we were trying with the sum of sigma I, sum of zi sigma I, let me erase this, was too naive, and instead we need to have a more complicated so I won't have time to explain this, but over time people developed intuition and then mathematical understanding of the fact that the Gibbs measure is going to organize itself in an ultrametric structure, and so you have to have an object that captures this specific ultrametric structure in here, and this more refined object, instead of being captured by a single parameter h, it will be captured by a measure, by a probability measure on the positive real line. And so, but in terms of formal manipulations, what you do is from this naive equation that you got, you just replace the naive parameter by a measure, and you find the equation that I presented to you at the beginning. Okay, and this I think is a general principle for any model. You write the naive equation and you replace everything by a measure, and you're done. Okay, so I'm running out of time, so let me conclude. I think the first message is that I think a lot remains to be understood. I presented the case with 2 layers as an example, but it's really one among many. There are plenty of the models where we don't understand what is going on. And I think, yeah, this point of view with partial differential equations, it allows us to synthesize previous results, and also to maybe clarify them, and to phrase new conjectures. Also to clarify the nature of the difficulty, whether or not the non-unitary is convex. We see that the model will be very different. And hopefully also prove new results. All right, so I mentioned one result which I think is new, which is about this 2-layer case, where I have one bound comparing the limit free energy with this equation, but I don't have the other bound yet. All right, so that's it for today. Thanks for your attention.
Hey, thank you very much. So we did have quite a few questions in the chat box, but we've got a few more coming. So Offer's asking, is it simple to write down the secret psi?
Yeah, so I think now you have a good idea of what you have to do. So you go back to this definition, and instead of writing this, you replace zi by some random field which is built from a real probability cascade, right? And you set t equals 0, and you set n equals to 1. The thing will not depend on n when t is equal to 0, and that's your psi. Does that make sense, Offer?
Offer, I'm going to try and unmute you just in case I cannot find you.
Right, I have him. So Offer, you can talk now if you want.
Maybe he doesn't want to talk.
No, perhaps not.
Okay. Are there any other questions?
Oops. Sorry. Is that okay? Can I speak now?
There you are. Yes, you can.
Yeah,
yes.
Sorry, I was muted locally. Do you, in that expression that you write now and replace the ZI, are those related somehow to the solution of tap equations or not?
I think not. So they are naive. So you don't have to fine tune them in some. You don't have to say, oh, they have to satisfy the tap equations, or you just write any. You don't try to match the parameters. You just have to make sure that the family. It's like when for query bias, I'm not trying to say I take H to be exactly the right mean magnetization. I'm just adding it and then finding relations between parameters. And in this case, it's the same. So I don't know if it makes sense, but maybe along the characteristics of the equation, you will see that the tap equations have to be satisfied or something like this. I'm not sure. I have not thought about this much, but when you define the object, you don't have to think about it.
So it's just a vector with correlations. That's what you're saying.
Yeah,
the
that's
ZI
right.
will be just a vector
kind of,
with a correct correlations.
That's right. That's right.
I see. Okay. Thank you.
Okay. Thank you, Offer. Are there any more questions?
Milton raised his hand, so if you locally unmute yourself.
Hi. Okay, so usually one way I see this type of results are useful is that because the PDEs are simple enough to give us additional properties about the original models which were hidden before. So do you think that this could be the case here, that looking at the PDE we can find new properties of our original models that could be useful?
That's a good question. So I suspect that in the case when the nonlinearity is convex and you can write the Hopf-Flachs formula, then the answer will be no, because probably the Hopf-Flachs formula is very convenient. In some sense, up to some change of variables, it was already known. So I suppose that in this case, there will be no additional information, except maybe you find better ways to understand how to prove convergence and maybe to find rates or something. But so maybe it's useful in the proof of convergence, but not in terms of finding properties of the limit. But in the case when the nonlinearity is not convex, then, well, in this case, I think there's no other way to talk about the limit anyway. So in this case, this is useful.
Okay. We have another question from Simona. Actually, I'm going to unmute you, Simona. You can ask your question yourself. You need to unmute at your end as well.
Okay, so that's very nice. And is there any hope to prove these, for these glass systems, to prove these freezing transitions from the PDE without actually having the explicit solution?
So at least I'm not sure if I'm very clear in my head on what is the freezing transition, but I only know how to do a very limited number of things. So I think it's easiest if I just tell you what I know how to do. So what I try to do is to verify that there is a transition from replica symmetric to non-replica symmetric systems. And so by looking at the PDE, you can check that when T is small, you will only look at replica symmetric measures, and when after a threshold you will need to look further away. But I haven't done any more refined analysis, which doesn't mean it's not possible. I only have done a few things.
But that's actually cool. So is the feature a shock?
No. At least in the model I understood, I think it's not. It does not have a singularities in the derivative, which was also surprising to me. But So this is something I don't understand very well, but my impression is that the way this transition happens is not causing a singularity in the first derivative. So the intuition from Curie-Weiss is a little bit misleading in this respect. I mean, it's not something I understand very well, but for a long while I tried to understand what is the structure of the shock, what is the structure of the shock, and then I thought, maybe there's no shock.
Okay.
Okay, thank you. Any more questions? Otherwise, we can wrap this up. Okay,